Is there any questions? So today we're going to talk about, in general, models. So it's like we're going to learn what we mean when we say modeling something in the context of human-centered systems and in general, just human-computer interaction, in general science. Okay? I am sharing my screen. I am recording. We all good. Okay, so welcome to week 4. Today, obviously, is about models. And before we get to anything, I want to show you a little bit of Fullmetal Alchemist. The rest is a bit gory, but you see what happened. So to reiterate a little bit, in the world of Full Metal Alchemist, alchemists draw these transmutation circles, and there's rules to it, right? And based on that, you can achieve something. You give something, and then you can change it to something. It sounds like science or the things we want to do. Here, what happened is that they were trying to revive their mother. And this is the very first of the season, so I'm not spoiling anything. And then what happens is that he loses his leg and arm. Alphonse fully is gone, and his soul is only bound to a metal. What's the word for the metal thing? Anyone can help? My English broke. The metal shell that Knight wears. What's the word for that? Armor? Armor. Yes. So, yeah, it's consequences. I think this idea that there's these rules and assumptions and you can activate it and then the circle does the work for you is basically the idea when you draw a flawed circle or you do something based on mistakes such as not having the proper sacrifice, you're making a mistake. Your model, which is the circle, is wrong. So it doesn't really know what you meant, only what you wrote. And again, there's no discretion, right? So I'm not trying to do like too much of a, I'm not trying to do too much of a comparison, but I thought it was interesting Another video example that someone else, Richard McClure, has used is a golem of Prague. Yes, but not only that, garbage in, garbage out, but that there is the models on their own. What I want you to get before anything is that models on their own are meaningless. It's how you use it, how you interpret it, and it's dangerous because they're powerful. It might tell you that something is good. Let's say it might tell you that vaccines are good, a model, right? And then it might turn out that you're wrong. Okay? Or we all build models. It might tell us that immigrants are the cause of all that's wrong in this world. And we build a model. We show a chart, and then we say, oh, look, immigration has risen, and then housing prices have gone up. It's a model. It's a correlation. But what are the other things, right? So the interpretations are powerful. The statistics itself doesn't know what it's doing. Okay, so essentially a model takes data and does something useful with it, right? That's what we're trying to learn in this data science class. You can summarize stuff, you can explain stuff based on how you think, you can predict stuff, forecast, you can classify things into different categories. We're going to learn a little bit of all of these, right? Before we get into the details and we get into coding, let's just try to think about models. Right. In general, we're going to learn about the inputs we're going to put in our model, right? In general, the input and then what model we give it, like the M, and then what output we have. Right? We're going to work with all of it. The input is something we've been working with EDA. We're going to learn feature engineering. We're going to learn different types of models. And maybe we learn a little bit on interpreting the outputs and using the outputs for something. Okay? So that's in general our approach to data science. But that was the ideal equivalent explained. Whatever wisdom comes out of it in the data and assumptions you put in, right? That's the idea. The model doesn't generate insights from nothing. It does not generate insights at all. You are the person that are making insights. So if you have wrong assumptions, the output will be wrong and it will be faithfully computed. The compute might be correct. So essentially, you're right. It is kind of garbage in, garbage out. It's basically equivalent exchange. Now we use the term hypothesis, and again, in quant methods, you might use it. Hypothesis and models are not the same thing. It's a verbal hypothesis is a verbal conjecture. For example, screen time harms well-being. Okay? It's vague, it's untested, and untestable as stated, right? We need to figure out what model we're going to use to test that. A model is precise, executable, and you generally need a model to test the hypothesis. They are not the same thing. Okay? So for example, your hypothesis might be screen time harms well-being, and then you might think about, okay, something to test it, some process model, okay, let's reduce daily usage time, or replace usage with other activities. Okay? And then you might also want to define what well-being is. And then you might have different types of models. You might build a linear regression on usage hours. We're going to learn a little bit on this. Or maybe you create a time series model. Or maybe you create a survey scale that tells you a score. But you might have a competing hypothesis that you never thought about. Okay? Passive use is worse than active use. Right? If you use it for something, it might not be as harmful. Or you might have a ton of different hypotheses. The same models might give answers to other hypotheses that you might not have thought about. This is very important in statistics, and we're going to hopefully learn a little bit on that. Even the intuition that when you say, okay, I have a hypothesis and I'm testing it, and you should be really careful in saying my model proves my hypothesis or reject the negative or the null of my hypothesis, because you just gain more confidence that your hypothesis is good and you gain less confidence, right? And because you need to have a really good scientific model of why you're doing the test, why you're doing the modeling, whether your model is good, then you can get there. So to sum up, the same statistical model can be consistent with completely different hypotheses. Rejecting a model does not reject the hypothesis. Confirming a model does not confirm the hypothesis. It might sound like a weird thing. We use it for that idea, but it's the process behind it that helps us reject or confirm it, or for us to gain confidence. It's a many-to-many relationship. So when you say I failed to nail and reject the null, doesn't mean that the null is true. And again, null is basically, let's say, immigrants cause housing market. Yeah, you can say evidence for and against. That's a good way to put it as well. But also in general, models is for testing something, right? Again, to sum up, we're going to have a whole session on statistics and get more deeper on this. But you build a hypothesis, you build a model that's precise and executable, and you gather evidence based on that model, which is our data observations. And then when it's consistent, you have your idea. I messed up. Okay. So always ask, what other hypothesis is my model consistent with? Essentially based on George Box. All models are wrong, but some are useful. No model is the world. All are simplifications. The question is never, is this model true? The question is it useful, and does it know its own limits? I will share with you after this in the website a lecture on this by Richard McClure that I'm using, basically the chapter of his book. It's really useful. It's really interesting narrative. But whenever you have a model that's confident beyond its design, this is a dangerous thing. And I'm feeling it right now because, for example, people build models of other people's attitudes. Like you have a model in your head and say, oh, if someone says something, then they are a fascist, and then that model is confident beyond what it's supposed to do, right? So we all do a lot of these weird models. I lost my I think I lost my Dungeons and Dragon dice, but later. But what are these models that we're talking about? There are different kinds. In the chapter you can read on it, but let's just learn a little bit. There are many flavors, and they don't all do the same thing. And before choosing a model, you need to know what you're asking it to do. So the two key questions: what is the goal? Do you want it to explain something or maybe predict something? Where does this structure come from? Is it from theory? Is it from data? So that in general, one way to think about models is to think about these theory-driven and data-driven. And in this class, we're mostly in this space, but we should sometimes think in this space, right? So you might have epidemiology models like SIR, which based on a world knowledge of theory of why a disease spreads, and then you can explain some phenomena. You can have a data-driven model where, for example, it can look at data and tell you, does screen time affect mood, right? But this is not a perfect way to think about it, because sometimes this comes from, let's say, a theory of psychology, okay? But it's data-driven because you base it on data and build that model. This might be like, and other models that are theory-driven could be physics models, right? Simulation models. They're not based on data. They assume something and then they go for it, right? Similar to these physics simulations, trajectory from equations, etc., right? And then there are these machine learning classifiers where you can predict churn from behavior, etc. So we have data-driven, predictive, explanatory, theory-driven. Not a perfect model to think about these. Again, even this is a model to think about modeling, okay? So it might feel too much like Inception or a dream within a dream or whatever, but it's a good way to think about it. So let's think about explanatory versus predictive. It talks about why does something happen. We essentially sometimes we care about the relationship between variables. Here, interpretability matters. We want to be able to interpret it, why something is happening. Does streaming duration cause viewer drop-off? Do we know? How do we test that? Predictive is generally, again, you could think about it as what comes next. We care about accuracy on unseen data. We want to say, okay, can our model do something when it hasn't seen a data? Can it, if tomorrow, if a new person signs up on Netflix, can it give them good things to watch based on other people's behaviors and their profile? That's a predictive model. Now, the mechanism for these can be a black box. We'll talk about it. For example, you can try to predict which sessions will end in the next 5 minutes. Or you can predict what is the day that the professor is more angry and why that might happen. So you can ask the same question, but use two different models. In explanatory model, you say, does stream length affect viewer drop-off? So you can have coefficients, significance. Again, it's about interpretability. It's about the way you ask your question and you design a study, and the scientific method here is important. But then there's a predictive model, which is about creating models that do something well. Which session will end in 5 minutes? And you don't care about explaining, you want to say, can I predict it? That's a way to think about models. So it's the same phenomenon. You can ask different questions, use different models, right? So the structure, whether it's theory-driven or data-driven, is another way to think about it. So the structure for theory-driven comes from domain knowledge, okay? So you encode assumptions about how the world works. It is interpretable by design because it's based on some deterministic things, right? An SIR model, which we talked about, assumes people move through susceptible, infected, and recovered flow, and then you use based on that. Data-driven, your structure and your understanding is learned from existing data, observations. Again, there are overlaps between these. They are not distinct. The model finds patterns without being told what to look for. It's flexible and powerful, but it can fail silently. A neural network predicting engagement from 200 different features. We will learn what this means, but you can have a model that looks at all user data and predict something that, hey, this user is going to commit a crime. Have you all seen that series that does that? There's a few movies that deal with this concept. The book describes another thing, deterministic versus stochastic. The idea with deterministic is a model that says, it's if an input exists, there's always the same output, right? For example, this is the idea that given a force and mass, acceleration is fixed, right? This is a deterministic model. Stochastic is a probability over possible outcome, usually. We've learned about probability distributions. You can say 70% of chance of rain tomorrow, and then you have, it's less likely for it to be 60%, less likely to be 50%, etc. So the idea is that it's demanding a single point prediction from an uncertain process, and it destroys information. Okay? So we have the deterministic answer. It will rain tomorrow. We have a stochastic answer. Again, not the best way to think about it. I'm doing this based on the book, but it's an interesting way to think about it. Okay? This is based on probability. Sometimes the answer changes, right? Because it's the model itself is based on random elements. And sometimes the model says I'm 170% sure is more useful than the one that forces to say yes or no. Okay. Now we're getting to classifier versus regressor. Classifier, let's try building one. Okay. So I can just record data. I'm here. I'm just saving data, classification. Okay. And don't judge me. I have many toys. Oh, no. Let's delete. We need a new label. Okay, and then here, I'm just going to say webcam. Okay. So we collected data on two classes. This is duck. And this is I don't know, Hello Kitty. Doesn't matter. So we have this label and we have data, and then we train a model on it. So it's doing it right now. It's going through iterations. I hope that it can do it fast. See, it's training based on the data. Now, it can classify something for you. It can tell you a duck, give you that this is a duck, and it can tell you that this is a Hello Kitty, okay? So it can classify based on image. However, it's a model, right? So if I bring this, it's still, the worldview for this is only Hello Kitty and duck, and it's still going to give you one of the answer. So now the model is 100% sure that this is Hello Kitty. Or let's see, this is Hello Kitty, or it's unsure, right? Because this is a weird color. That was classification. You have data, you train it, and you ask it to classify the input for a certain output. And you can have multiple classes, and you can also have duck or no or something. So output is a category. Is this comment toxic? Yes or no? Which genre does this stream belong to? Gaming, IRL, music, and regressor, the output is a number. How many viewers will tune in this hour? How toxic is this comment, for example? So different output type, different design, different failure modes, and different evaluation metrics. So for classifier, we have different types of algorithms, but the idea is that you evaluate it by accuracy, precision, we'll look at it. And for regressor, you evaluate it by error rates, or mean squared error, or root mean squared error, etc. Okay, another way to think about models, again, these are all the different ways you can use different knowledges of different types of models that you want to have. A black box model is one that is not interpretable. But let's think about it. If you can read off why the model made a decision, then that is not a black box model. Linear regression, for example, each coefficient has a clear meaning. We're going to learn about this. Decision tree, which we're going to look at, follows the branches. A black box model, it works, but you can't easily explain how. Neural networks or all the chatbots that you do are black box. You don't know why. You've designed it, but you don't know why a certain word is the output. There's a lot of weights, no clear narrative. Let's choose a model type. Essentially, there's no best model for your weight. You need to say, what are you trying to do? How much data do you have? Do you care about uncertainty here? And how will someone be affected by this decision? So this taxonomy is a thinking tool for you. It's not a checklist. It's about for you to know when you go into the world and want to build a model as a data scientist, what type of model am I thinking and how am I looking at it? We're going to look at evaluating two specific kinds of model. About did the model actually work? Because building is half the job. Knowing how it actually worked is the harder thing to do. And the answer I'm repeating, it depends entirely on what we ask the model to do. Okay? So we have these two sets. Statistical explanation is about why does this happen? Does the model fit the data? Are the relationships meaningful? The ML prediction is that does it generalize to new data? So essentially, before you run any stats, define the question. Before the model, right? You need to know what you're going to do before it. You need to define what is the construct you're measuring. How is it operationalized? What would be a meaningful result? Running model without this is like measuring with a broken ruler, essentially. So again, you think you set your measures because you need to say, okay, if I build a model, how am I going to evaluate it? Have you heard of the term p-hacking, for example? They build models without deciding what the theory, what the model construct is. So this is your evaluation chain. You ask a question, what do we want to know? And then you have a construct. What concept are we measuring? You do the model. How do we operationalize it? And then you interpret it. This is your chain. The skipping, you don't want to skip any of these, okay? So for example, does increased Twitch stream length lead to more viewers dropping off? That's a question that you're going to ask. And the construct is viewer engagement. But what counts as drop off? Leaving midstream, not returning next session, both? That's a question you need to ask. And then how you operationalize it. Average viewer retention rate per stream, binned by duration, for example, might be your measure. And then your model could be linear regression, and then you can say retention causes duration, for example. And then interpretation is that a negative coefficient means longer streams lose viewers on average, but how much matters and for whom also matters. So for explanatory models, the first question is how much the variation does the model account for? And we measure it with R2. Again, we're going to have a whole session on this. We've seen this also before, means the model explains all the variations in the outcomes. If it's 0 or like 0.5 means it explains nothing. And the model fit looks like this, right? The differences between a point and how we fit a line is a residual. These orange dashes. These are the gaps between what the model predicts and what actually happened. Smaller residuals means better fit. Okay? Just try to think about this conceptually for me. And I want you to know that fit is not enough. A model can fit training data perfectly and still be useless. If the model is too complex, it memorizes the data instead of learning from it. So that's what we call overfitting. We're going to see examples of this. An overfit model, when it sees new data, it might fail because it only knows the existing data. That's why explanatory fit metrics alone are not sufficient. We need a separate strategy for evaluating generalization, how good the model generally is. That is what ML evaluation frameworks is for here to help us. So I skipped F1 for now. We're going to learn for it later. But let's think about classification. Which category, right? Regression asks how much? How many viewers will the stream get? How long will a user session last? What will the engagement score be? I'm giving you a lot of examples to think about. And then, because in regression, we can't use accuracy. For classification, we can say, oh, the model is accurate 95% of the time. But here, we can say how far are we from that number that we should have predicted. We need measures that measure error. Okay? I skipped classification. Why is it? My slides jumped. So sorry. I'm gonna track back to because I realized that I should have talked about classification first. So let's talk about classification. I showed you what classification is, right? What is a good classification model? Am I? Yeah. ML models ask, does this work on data I haven't seen yet? A model that memorizes training data looks perfect but is useless. We need a principled way to test for generalization. Okay? That is the model that we do for any sort of classification task or regression task, right? We bring it, we have a lot of data, right? We create a training set and we create a test set. Okay? The training set, the model learns from it. The test set is held back and never touched during training. Okay? Performance on the test set tells you how model does on unseen data. Why do we keep a test set? For example, a student who memorized last year's exam will score 100% on last year, but if we give it a new exam with new questions, you will never learn what they have learned, right? The test set is the exam with new questions. If you peek at the test data during training, you've spoiled the exam. That is the most common mistake in applied ML, right? So you train only with training set. You then use a test set to test it, and then the validation is to tune, and sometimes we have this validation set that is for tuning and improvement. When you want to iterate, the test set is basically sacred here. Use it once at the very end. So now, what is a metric? Accuracy. So if I have, let's say, 100 data points in the test set, right? And then I have bald or not bald as the classifiers, as the categories. And then if there's 50 bald and 50 not bald data points in our test set, if it categorizes both balds and not balds at the same time correctly, then it will have an accuracy of 100%. Accuracy means how many correct predictions, how many total predictions. What fraction of predictions were correct? It's easy to compute, easy to understand. For example, model predicts viewer will return tomorrow, correct 82 times out of 100. So the accuracy is 82%. But why can accuracy lie? So imagine a disease only predicts 1% of the population. If we create a model that always says no, it's a very simple model. It just says, whatever input you give me, I'm just going to say no. It doesn't matter. It's a function that says, hey, define function, input, data, output, always no. If only 1% of the population has the disease and the model always says no, they don't have it, the model is 99% accurate. And that is the problem with accuracy. Okay? If the model that always predicts healthy no matter what is 99% accurate, is that a good model? No. It has never correctly identified a single sick person. And that's what you care about. Accuracy is misleading whenever classes are imbalanced. So in that 50-50 example, accuracy is good. But if you have an imbalanced class, accuracy can be misleading. So that's why we use the confusion matrix, okay? Because it confuses you when you do this. Okay, and this will be one of the exam questions. So just know for now. In confusion matrices, we basically want to ask, oh, the chat just updated. Okay. Sorry, I got distracted for a moment. Okay. So the actual part is what the reality is, the truth is, and this is what the model predicts. Okay? So if the model has correctly for the things that are, so let's just say bald here and not bald. If the model predicted bald correctly, it's a true positive. Correctly said sick. The true negative is the one that the model correctly said is healthy. They're healthy. So the model, you want to say the model says bald or not, healthy or not, sick or not, you have to define it. And the positive is the one that says yes. The negative is the one that says no. So these are the wins. The model got it right in both directions. The false positive is interesting because they are negative. The model is by mistake saying that yes, the person is sick. So you've learned about this during COVID. The in-house test could say you're sick, you might be not, or the other way around, right? The house sick, the COVID test could say you're not sick, but you actually might be sick, or you might be COVID. So these are the mistakes, right? False positive is when the model is saying something is positive and the actual data is not. Okay? So just remember this. Always draw this 4 parts for yourself and see what happens. Okay. These are the missed cases. The model said negative, but it was wrong. Also caught a type 2 error. Okay? So the example is disease screening example, 1,000 patients, disease prevalence is 1%. This is the example where the model is accuracy is 99%, but the model found 0 sick patients. This is what we care about. People will die with this model. That's why you say data science is dangerous, right? So what do we do? Use precision. Let's bring in precision, recall, Wikipedia. I love this diagram. Okay? So with you remember what true positives are? Precision is from the ones that you predicted positive, how many have you correctly? Even now, it's hard to verbalize it. So let me clear. So it's true positive divided by true positive plus false positive. Of everything the model predicted as positive, how many actually were? This is your precision. High precision means few false alarms. Okay? So draw this diagram for yourself, and this is your precision. When false alarms are costly, for example, spam filters and content moderation. Flagging a professor's email as spam has a real cost. The recall is of everything that was actually positive, how many did the model catch? Okay? So precision is of everything that model predicted positive, how many actually were positive. Okay? So if I, of all the ones that I said people are sick or people are sick, how many did I get correctly? That's my precision. And from all the ones that were sick, how many did I get correctly? So true positive plus false negative. High recall, few missed cases. Disease screening, fraud detection. So this is recall. These are all the relevant elements that you care about. You want to get all of these correctly, and you want to get these, you want to increase this. That's your recall. How many relevant items were retrieved? How many retrieved items were relevant? Always go to Wikipedia to get this. So you can use these diagrams as cheat sheets for yourselves. Essentially, improving one tends to hurt the other. Which matters more depends entirely on the cost of each type of error, right? You never can get too perfect. But there's also a model called F1, which is basically balancing both. It's precision times recall divided by plus precision plus recall. Because it's one number that respects both precision and recall. The F1 score is their harmonic mean. It punishes extreme imbalance. A model with precision 1 and recall 0 gets F1 equals 0. Use F1 when both false positive and false negatives matter. Okay? We're almost done. Now, for predicting numbers, again, we're going to do a lot of this, but just try to remember that we measure error, right? We have an actual number, you have a predicted number, the residual is the difference. Actual minus predicted. Positive means we underestimated, negative means we overestimated. Okay? So how do you calculate this total model problem or error? One thing that you can do is mean squared error, because this essentially you average all the residuals. If you just do that, they cancel out because they're going to be below the model and above the model, below the line, and you'll have some negative and some positive predictions. That's why you averages it. That's why you square each residual first, because everything then becomes positive. Then you square the two things, removes the sign, and punishes large errors more. Okay? A single bad prediction can dominate MSE. Mean squared error is your metric. So yeah, the area of each square is a squared error of that prediction. MSE is the average of all the squared areas. But we use something called root mean squared error. Is in squared units hard to interpret directly when you take, for example, if yours are in 1,000, MSE is in 1,000 squared. But if you take the square root to get back to the original units, you can then measure. For example, 8K means predictions are off by roughly 8,000 viewers on average. Root RMSE. It's the same scale as data, directly interpretable. Still sensitive to large errors because of the squaring step. You also have mean absolute error. So you can take the absolute value of the error and you can take the mean of it. You can just take the absolute value of each residual. Every error counts equally, no extra punishment for large ones. More robust when the data has outliers, but essentially you generally want the punishment for larger errors because you want your model to not get really bad errors. It's easier to explain because 8K means predictions are off by 8,000 viewers on average, but the outlier problem, right? That's one outlier. The mean absolute error is 17. The RMSE is 30. This will punish the models when you're training them. Okay? Choose based on whether outlier represent real signal or noise. So last slide, before this is just an intro for the rest of the semester, essentially, for many parts of the rest of the semester. You can take mean absolute error. You can use MSE and RMSE for many of your models. There are a couple of other things that we can do. There's like ROC and AUC metrics that we're going to learn later when we actually do the models, but they use the same concepts that we have done. We covered a lot of stuff, so you should all go and read the chapter. Rewatch this when I post it. Let me know if you have feedback or comments, or if you have questions, we can think about it. And good luck on your assignment. And I promised 30 minutes, but it's about 50 minutes, so apologies for that. Any other questions? So yeah, in general, what we learned, models, you need to think about what models you use, basically. All right, bye.